gradient. Okay, the surface gradient J here Fz to the K. Okay, this is del F partially differentiated to the X, partially differentiated to the Y, partially differentiated to the Z, K. Okay, but can you notice this is a vector? Okay, this is a vector. Therefore, the definition of gradient is nabla F. Okay, when you use a nabla F, we are referring to the gradient of scalar functions. See, we are identifying the gradient of each scalar function in the vector form. Okay, can we visualize this nabla F, the role of nabla F here? Okay, the role of nabla F can be okay. When I say this is a smooth surface, everyone will agree with me. You'll say yes, this is a smooth surface, but actually it's not. When I try to give some kind of idea here, you see, I'm trying to put it here, something like this. But when I start sketching like that, then immediately you know, oh, there is this is not a smooth surface anyway. Okay, there is a something, the curve exists inside the surface. Therefore, can I able to monitor this changes in this surface? It's not anyway, it's a smooth. Therefore, how to identify the smoothness of this surface? Okay, this is only possible to get it through what we call as a gradient. Okay, now you can see here, this is a normal surface. As you all know, we call it, this is a normal. Okay, I call it that as a N. Okay, in normal circumstances, okay, the surface is must refer to this, right? This is, we are referring to the normal. Okay, we refer to the normal. But there is an angle. Actually, the surface is actually moving into this directions. We call it that as a del F. And there is an angle exists like that. That means, I will show you, okay, it's something like this. Okay, you can see this, when I refer to the normal, I'm referring to this. Okay, I'm taking the pen and just, okay, but when the surface is not a smooth anyway, you see the angle is moving in a different directions. When I put it here, it's already in a different direction. Okay, slightly there is an angle exists. That means the surface is already, there is a curve exists on the surface. Therefore, the role of the gradient is basically to identify the changes, the smoothness of any surface. Okay, now therefore the del F is, you will say, is an angle between, okay, between its corresponding normal, or we may say, I'm just say in the direction of a point. Okay, if we pick a point, then we know, okay, it's actually there is an angle exists there. Or we may say again the points to the direction of greatest rate of change of F. This is the surface of F. Remember, this is the surface of F. We are trying to see, okay, maybe I may say the surface is smooth, but no, I'm trying to see there are some greatest rate, direction of the greatest change, rate of change can be monitored. Therefore, is there any possibility for me to see that? Okay, yes, possible. We able to monitor, see the directions. There are field for particular point. Let's say I pick a 1 point here. Okay, when I pick 1 point here, P, call it as P. This is a surface. Okay, derived from the fxy equation. Okay, with this equation, if I choose 1 point, can I able to see this is always I put it as a constant lah. Okay, it's a constant referring to a one function. Could take it as a constant because it's a flat, right? It's a flat surface. When I refer to the flat surface, it look like a flat, but assume, let's say, assume when I refer something to the normal here, okay, there is a some, if it is not a constant here, then you can see there is a something del f will exist. Okay, del f will exist here, and this particular change will be addressed as the C point to the direction of the greatest rate of change. Okay, how to understand this? Okay, how to greatest, the meaning of this direction of the greatest rate of change. I'll try to give you some idea. The greatest change, let's say we pick several points, then we know already. Okay, let's say this is the point. Okay, I pick certain points here. Okay, this point is referring to this site. Okay, the another point is is like that. Another point is something directing towards this. Okay, another point directing in this angle. Okay, we know the surface is a normal, right? When we say it's a normal, this is a normal. Normal is a straight line, but it's slightly, there are some angle exists between this vector. But what is direction of the greatest rate of change? When we define points to the direction of the greatest rate of change will be detected by the del f. The del f, we can see almost all the lines here, could be some could be like that. Okay, we can see, we can find out the greatest change means the greatest angle that it can cover. Okay, the greatest angle that it able to cover. In this particular case, this is the greatest angle that it already covered. We are not picking 1 point, but particularly in this particular point is this is one of the greatest rate of change. It's not particularly we are referring to one single point here, but we say overall. When we see this is, we call it as a field effect. Okay, field effect. Normally the field effect will be like this. Okay, we see when I say there is this particles is actually moving. Can you see this? Okay, you may say, oh, this particle is moving in these directions. Yeah, you're correct. But okay, slowly you can see the particle is moving in this direction. Therefore, you may say, oh, actually the particle is moving in this direction. Therefore, what is the greatest rate of change? Okay, the greatest rate of change is moving from here to this directions. Can you see that? Therefore, this is what we call the direction of the greatest rate of change. You can see this is changing, slowly changing towards this. Okay, therefore, the del f able to cover that. And the nabla f, the modulus of this will give you, its magnitude is a magnitude of greatest rate of change. Okay, greatest rate of change. Therefore, when you use this, you able to get the magnitude. Okay, the magnitude. In another term, you are getting the magnitude of the greatest rate of change of this particular object. Okay, now if I say this magnitude, we are using the similar method as square root to fx. We are taking all the squared to y squared fz squared. Okay, this is what we call it as a del f p. When we refer to the p, the magnitude can be calculated based on this. Therefore, in a simple message that I may say is a direction on the derivative of a given point. Can I make it like another simple point here? Say that what is nabla f? The gradient can be explained as this gradient f can be explained as something. One is an angle, okay, angle of that cube. One of the things is a very important information that I want you all to actually it's not exactly, it's actually I'm referring to the angle. Okay, nabla f actually is referring to the angle, the change that is making, okay, direction of this, because since this is a vector, remember, it's not referring to the angle, but I'm trying to say in order to understand the nabla x, actually it's a direction, it's a vector of the greatest rate of change, where it will able to give you the angle. It's not equal to this, remember, it's a vector. Okay, now with that information, let me give you one simple example. This is very simple to calculate. Okay, simple example. Okay, example 1. Okay, example 1. Find f if f equals to sorry okay, fx, you try to differentiate that, is a 2x. Okay, this is a partial differentiation, remember, it's a partial differentiation, and fy is a negative 2y. Therefore, the combination of del f here, nabla, can be explained as this: I del f to the del y to the j. You just place it back, is a 2yj. This is actually gradient, basically is a field effect of vector. Okay, it's one of the field effect. We can monitor the change of the rate of change of the greatest changes in the points. It's a very interesting. We can visualize this. If you got a if you wanted to see some good examples, you can see some YouTube videos whereby they may show you with the video clips with the field effect. That may give you a better understanding how the gradient, okay, the gradient of the vector really work in the actual scenario. Okay, now I'll give you another one more example. This is a simple example. You may say, wow, very simple. But yes, it's really simple. But I'll give you one more scenario which will give you a better clarity. Okay, better clarity of the this gradient f. Okay, let t be a x, y, z to 10 e to the negative r2, okay, where r squared is x2 plus y squared and z squared. Okay, this means I'll give you the scenario. Most probably you're able to get it, the scenario. Based on the scenario, let's say this is, they want you to find del t. This is a simple question, but let me connect, okay, and find this, and I'll put this one more notes here. Say you just explain what is this, what is going on. Okay, how to explain this, how to elaborate these logics of this question. Okay, first of all, you try to see this. Okay, what is this? This equation. This equation is referring to the spherical. Imagine there is you're moving, okay, you are inside a room. Okay, you got a one what do you call, okay, account system. on the top of the ceiling. Okay, or maybe I'll try to put it in the middle. At least it's sorry, I put it in the middle here, in the middle of this. Normally it won't, right? It's not practical, but I'm giving you an idea. Okay, or maybe heater. Okay, could be a heater in the middle of a room. Maybe I call it this as a room. Okay, when you see this Rx x2 is in a progress state of that, okay, that means it's a ball, right? You can see this is a kind of ball effect, okay, a spherical effect. You can see this is a spherical. Okay? This is a spherical, but we are combining that to the exponential, and there is a negative. You will try to explain that what is that negative means here. Okay, there is a heater. Okay, when there is a heat coming out from this point, the heat actually is moving, right? Okay, the heat is moving, spreading, okay, spreading in the rooms. Okay, is there possible for me to identify the spreading of this heat and the source of the heat? Of course, it's spreading. Actually, spreading means it's moving away from the source. When you are moving away, it means it's a negative. Okay, moving away. Okay, it's a kind of progress, but slowly you can see at this particular point, surrounding this point, all the heats are okay, the density is very high. Then slowly you can see the density, over here is less. That means it's the spreading. Once the heat spread, move forward away from this point, we can see the what you call the field effect is getting smaller and smaller. Okay, therefore how to calculate? First, let us calculate first. If we wanted to calculate this, just say del t can be okay, I just take out that as a 10. Okay, I'll just say 2x. You just substitute here r squared, okay, r squared, yes, is a substitution of this 2x. E negative r squared I. R squared is a referring back, right? That means is a when I remember, just very simple. Don't panic here. When I use a nabla, I'm using d dx to the r. When I use this, remember z2, what am I get? I'll get here 2x. Remember, when I just differentiate this, okay, this is a del, not a d, sorry, it's a del, partially differentiate the x, I will get a 2x. Okay, similarly, I get a here, but isn't a, I think I miss, it's okay, negative is there. Okay, of course, I need to represent that in a negative form. Okay, overall, if it is a negative is here, then negative will come out. Then I just write the negative here. Okay, it's a negative here. Then overall, I'll get it this. And similarly, I get a 2ye negative r squared j plus 2 what do you call ze negative r squared. Okay, nabla t will explain the detail. Okay, what is this? The nabla t actually will give you the field effect of the rate of change, the direction, the change of directions, of T, the temperature. Okay, you can take it that as a temperature, the temperature. Therefore, you are able to see that in this case, for the gradient field, how to explain this when I say T. Can I explain this? Yes, you need to explain first. This is the magnitude, basically what I can say, this is the magnitude. Can I say this is the magnitude? Okay, the magnitude. Of course, we know this is the magnitude of t. But can I explain that in some detail explanation? Yes, maybe I may say that is at the gradient field. The gradient field will explain the changes of this room temperature, and the magnitude, basically the magnitude of that changes at heat source. Maybe I need to pick a one point here, then only I able to calculate that in a very specific way, right? Okay, magnitude of course is very difficult, very hard to find the magnitude of this, but actually I can explain. Okay, I can explain to the heat source. Okay, the gradient field will explain the changes of this room temperature and this one, and this magnitude, the magnitude of that changes of heat source can be explained as this, the del T, right? The T increases near the heat source. Okay, heat source, but decrease when it's far away from the heat source. Okay, maybe this is one of the way to explain the idea of the movement of the flow. Okay, the flow or the gradient of the temperature. Okay, increases near the heat source. Okay, it's moving away. How do I know it's moving away or moving towards? It's a negative. Negative is clearly is understood. Negative means it's a moving away. Later we will see what is the convention of negative and positive in the divergence. When we see that it's a convention. Anyway, you wanted to put it that negative into a moving towards also is possible, but it's a collectively a convention is a negative means it's a moving away, and positive means you are attracting force, right? Something attracting towards you, that means it's a positive. Okay, coming towards you. Okay, with that we have done gradient. Okay, we have done the gradient. Okay, now okay, okay. Can I move into one more topic? I have 18 minutes to cover the directional derivative. Okay, directional derivative is another important component of vector, whereby you can use this directional derivative to identify many, or to calculate, okay, to calculate the force or the value of a particular object in the in the not a smooth surface. Okay, not a smooth surface. Maybe I'll try to give you one example here. Not to say example, first let me define what is a directional derivative. Okay, f naught to the y naught to the z naught can be defined as, this is a different books definitions. Actually some books they will define as something d, or d means it's a directional derivative, b means it's a unit vector, whereby we just define this as with the unit vector. This is a unit vector. Okay, overall we end up here as a scalar. Why it's become a scalar? Because you must understand this. When I say scalar means it's a one value that actually will carry the value. It never carry the direction. Okay, therefore del f here is a vector. Okay, this is a unit vector. Okay, dot product to that I will get a scalar. Okay, in a simple understanding, just I want you to grasp this logic first. Okay, there is a del f. Imagine there is a f, del f here. Okay, del f here. Okay, this might be in a one direction, no problem. Okay, could be in a different direction. And let's say there is a b. Okay, b. Okay, I'm taking a one unit vector. Okay, unit vector in a one particular vector in a one direction. Okay, in a one direction. That's why we call it, this is a directional derivative. Can I dot product? When I start dot product with this, dot product means, can I make it this both moving in the same directions? Okay, moving in the same direction. Okay, moving in the same directions. Okay, I call it, this is sorry, nabla. Sorry, this is nabla. Nabla f moving in the same. I just, because I want you all to see parallelly. Is it, can I observe this in a parallel line where I can see both in the same direction? When I do that, what is the significance of this? I able to calculate the value of this f in this perspective. Okay, in this perspective. In this means here, okay, in the unit vector of b, I able to calculate the del f in the direction of b unit vector. Okay, what is the idea? Okay, I'll try to sketch one more sketching here. It may give you some more better understanding. Let's say there is a sky. For example, there is a sky. Okay, sky, the cloud. For example, the cloud. Okay. The cloud is cloud is always is a straight, and okay, you are walking, okay, down, okay, mountain. Okay, you are walking down the mountain. Okay, this is a kind of mountain you are walking down the, okay, climb down, okay, in the mountain. Okay, now let's say I call it this as b. Okay, unit vector. I'm using this as a unit, smallest unit. I'm picking this direction as the smallest unit, and I wanted to calculate one single point of f here. Okay, I call it that as x, y naught, z naught. I'm just choosing one of this point. Is it possible for me to calculate the impact, okay, of this f on this directions? Okay, therefore this in the another scale, maybe I will just okay, I sketch this in this way, is easier. This is in the b directions. Okay, I sketch that the cloud, I'm taking the point, the cloud actually representing the y, z, and can I map it to this bz, to the b what do you call, vector? Okay, this is a one very interesting phenomena, okay, which I can capture based on the directional derivative. Okay, the good example, I'll just say, maybe just I give you one example. Find directional derivative of f through y2 at the point, maybe I call it, this is a two dimension in the direction of p moving to q z. 611. Okay, now can I identify PQ? Okay, the direction, the direction vector of PQ. Yes, this is can be simply calculated by just say 0 I, because we are using I and J only here, and 11. This is a simple question actually. Therefore, now I know this will be represented in a 6i and 11j. PQ is a vector where the 6i and 11j we calculated based on the points given to us. Okay. Using that, can I identify the magnitude of PQ? Okay, because over here we need a unit vector. It's not a vector. Okay, we need to identify the unit vector. The unit vector of this will give you 6 to 11. Here we get 157. Therefore, what is the unit vector of PQ? Unit vector is a vector of PQ divided with the unit vector of PQ. Okay, now how do I calculate del F? How do I calculate the del F? The del F is Fxi, Fyj, Fzk. This can be calculated based on F. You can see x2 to the y2i, remember, 2yx3 to the j. And we already learned before, jj, I, k dot product with the k will produce 1. But if you combine different combination of the coordinate position, or coordinate, not a coordinate position, maybe the unit, vector units, you will get 0. Okay, j to the k, you will get 0. J to the I, you will get a 0. Therefore, when I combine the PQ with the D, PQ, F, X naught, later we able to calculate. Let me show you the PQ. Now, it can be explained as this: 3 x2 to the y2i plus 2yx3 to the j. Okay, 6 157 I 11 157 j. Okay, which will give you in this case, okay, you see, I to the I, j to the j. Okay, ij, you will get 0. Therefore, you no need to calculate this too. Okay, it's become 0. I to the I, j to the j. That's it. You will get here 18 x2y 157 plus 22 157 x3y. And when you substitute that with the what do you call D, PQ, F with the -1 and 1, you will get the answer is 4157. Okay, this is one of the simple example how to calculate the directional derivative. And you see, I've taken a long time to explain all these simple things because this required some kind of understanding, and this can be done within 10 minutes time, very fast. Okay, I can explain, okay, this is the formula, this is what you can get it. but I'm not interested to do that. I know it's a little bit because I'm trying to emphasize to you these logics. I want you to understand this logic, because these all simple things. Actually, you can see this is the directional derivative is a scalar. Okay, when I say scalar, you must take a full notice on that. Why it's become a scalar? That means in this particular case, we are trying to see the value of this point. Okay, when I see this from here, if for example it's giving us some kind of impact to me, or okay, let's say to me, this is the value that it will give me. It's a scalar value. Okay, the relation is a scalar, it's not a direction. Okay, therefore you must remember, in simple term, we are trying to see, okay, gradient referring to the field. Okay, extension of the field, we are trying to see the field. Field means here is the changes overall. Okay, we are trying to see the overall one by one. Okay, the movement of the particular particles in the field. Okay, in the field, but directional derivative is a different from that, where you can able to calculate the value of that. Okay, I'll give you another example, one more example, in order to get a better clear understanding on this. Okay, you can take it this as an because this 3 example is good enough for you to do any directional derivative questions. I'm going to give you 3 example only, but the 3 example will cover almost all the problem related to the directional derivative. Okay, you can see that can be another one more model that which they will use to ask you the questions. Here is x2 yz to the 4 at 1 -2 -1 in direction 2I minus j plus k. Okay, imagine this is kind of still, we imagine this as a straight line. You must remember what I mean by straight line here. Okay, when you take it, this is a 3. Okay, you call it, you see, I, x, z, y, j. It's not a curve. You can see this is a straight line. When we see this, it could be I means is this is x, I means is here 2, -1 of j, negative means here at this side, and k is here. That means it's basically, let's say I put here, okay, I put here, this is the point that we are referring to, the direction that we are referring to, 2 I j k plus k. That means the reference point is somewhere here in this case. Okay, this is still straight line. You can see we are referring to the straight line. Okay, straight line, therefore we need to use a unit vector. Can I calculate this? Yes. Okay, we know, okay, the points already given